here. Stop sharing, and let's try another one. Multiple choice, launch poll, and then we're going to start. So this is the first one. Now say for each question, you have 1 minute, okay? So we need to have some limitation, otherwise it will take very long time. Oh, by the way, we got around 20 students registered in total. Today, I don't know how many of you are here. Seems like we got something like 18 because a few of you like got sick or have some other reasons who couldn't take it. The poll tab is blocking it. Oh, so let me think about that. If this is not a story, how can I? Oh, you can move the poll tab. Can I? Is it moving? Oh yeah, you can move the poll tab, right? You guys can drag the top bar. Okay, great. So we got 13 answers. Let's wait a few more seconds. Please be fast. Great. Yeah, the first class, we will, have some technical issues, but then we'll figure it out. Okay, most of you choose B, but actually the answer is A. Now briefly talk about this. Why is A? Because this is copper sulfate. Can you see my writing? So basically, the reaction is copper sulfate reacting with barium and hydroxide. And then these two will produce two precipitates. One is copper 2 hydroxide, which is a blue precipitate. Another one is barium sulfate, which is a white precipitate. So when we have a mixed precipitate, you will see the color of the dark one, right? So which means the white one will be blocked. So you will see the blue precipitate. So the answer should be A, okay? Not a bad beginning. So let's try the second one. Relaunch the poll, allow yes. And then let's try the second question. You guys ask a great question. How am I supposed to know copper hydroxide is blue? Actually, all of the copper 2 plus either salts or precipitates will have something similar to blue, because this is the color of the copper 2 plus, right? So which means a lot of complex ion of copper is blue. The copper hydroxide is also blue. But a special example is copper 2 oxide. This is black, is a black powder. So except this, I believe most of the other copper 2 plus are blue. Okay, this one is pretty straightforward. I think most of you got it. So I'm not going to wait. I will share the results. All of you choose D. I want to say a few more words about the question. Actually, there are only two elements which are liquids at room temperature and 1 atm. One is mercury. Another one is bromine, Br2, right? Because we are talking about the element. So methanol, obviously, due to the hydrogen bond, although it's a small molecule, but it's a liquid at room temperature. Iodine, we know, is a kind of a dark purple solid. Actually, if you see it from the bottle, it's kind of black because it's too dark. Okay, next one. Okay, let's wait for 2 more votes. One more. Okay, I will stop here. If you guys have no more response, it seems like we got 19 students, but only 16 of you are alive. The other 3 probably you are playing video games. I don't know. Okay, share the results. So most of you choose B because B is pink. So which means B is the correct answer. And a very typical experiment is if you add chloride to the system, it will change into another complex, which is blue. This is a very typical experiment in AP chemistry to demonstrate the idea of equilibrium and also demonstrate the idea of the Shelterless principle, right? So A is colorless. Why is colorless? Because the ion is silver 1 plus. And if you think about what is the electron configuration of silver 1 plus, I think you can figure it out, right? It will be 4d10, which means the d electrons are 4 filled. If you know some idea about the dd transition or the crystal field theory, you will see all of the d orbitals are filled. So which means there's no way for the lower energy electrons to jump onto the higher one due to absorbing the light, right? So this is why in AP chemistry, there is a very typical question, which is called zinc 2 plus is colorless. Because zinc 2 plus is also 3d10, kind of fulfilled d orbitals, right? So I think even you don't know any idea about dd transition or crystal field theory, you need to know when the d orbitals is fulfilled, is colorless. So this is why silver 1 plus is also colorless. So similarly, mercury 2 plus, because it's in the same group as zinc, cadmium, mercury. So all of those kind of 2 plus, they are colorless. The last one, it is kind of color, kind of reddish brown, but is a solid and also is a precipitate. So which means you cannot dissolve it in water. So you cannot use spectrophotometer to do the determination. Make sense? Let me know if you have any question, okay? I have 6 questions in total. We need to hurry up. Next one. We got 20 students now. Obviously, the answer of this question right now we got is very diverse. By the way, when you get a chance, may I ask all of you to change your name into your official name, and then for me to recognize who is whom. And also do the change in the Google Classroom and your Google profile, okay? Okay, well, we'll see. We got 17 answers. Most of you choose C. Actually, C is the correct answer. So the reason why C is the correct answer is because A is acidic, right? Because aluminum 3 plus is the conjugate acid of a weak base, right? So it will have the hydrolysis. Although different textbooks use different strategy to explain, I prefer to use something like this to explain. This is called hydrolysis. Some of textbook, especially Zandel, they will like to use this kind of strategy. These two are the same. These two are the same, pretty much the same. Give you the same answer. The solution is acidic, right? And B is neutral because strong acid, strong base, right? Both C and D are basic, but why C is more basic? If you compare the conjugate acid of these two, can you tell me what is the conjugate acid of the last one of D? Actually, this one, right? Do you know what this? This is the formic acid. if you show the structure, it's like this. So it's an organic acid, it's carboxylic acid. And we know carboxylic acid is stronger than carbonic acid. This is a stronger acid than carbonic acid because when you add some vinegar on the eggshell will dissolve and produce a lot of bubbles. So this is a great demonstration to show you carboxylic acid is stronger than carbonic acid. So which means if the acid is stronger, which means the conjugate base is weaker. So yeah, if the acid is weaker, the conjugate base is stronger. So this is why C is more basic than D. I think most of you got it. So let me kind of very briefly explain. Okay, we got 16. One more, two more. Hurry up. Okay, most of you choose C, which is a correct answer because this is a burette. Burette is a precise volumetric glassware. It's called precise volumetric glassware. What does it mean? Which means you need to estimate one more digit. So here, this is 30.3 milliliter, and then you need to estimate one more digit, so which means you will get two significant figures after the decimal point. I got a question. You could see difference in energy of the two sets, but they're too complicated. Kenny, the question of the basicity is not related to kind of how many H plus it can got. Now say I will try to give a little bit more explanation in the Google Classroom after the class. Okay, I have to move on. Yes. Okay. So next one. Obviously, if you choose D, is wrong, right? Because you will figure it out by yourself. The last one, guys. Okay, I got 60 answers. Most of you choose D. D is the correct answer. A and B, right? All very obvious. The first one, after you add the H plus, it will change into magnesium 2 plus and water. The second one, it is an amphoteric oxide. So when you add the H plus, it will change into aluminum 3 plus and water, right? Dissolve. The last one, it will produce a weak electrolyte, and this weak electrolyte is unstable. It will decompose into carbon dioxide and water. So all of the ABC will be driven by the weak electrolyte, the production of the weak electrolyte, and then the reaction will go to the right side. The last one, you have no kind of driving force for the reaction. Okay, so let's stop here. It seems like the questions I prepared is slightly easy for most of you. Actually, I kind of slightly revised those questions based on the national 2017 and 2016 question number 7 to question number 12, which is related to the descriptive chemistry. I would like to know whether you like it or not. If you like this kind of idea to have a warm-up pop quiz before we start, the contents of the pop quiz will be related to the contents we are going to talk. If you like the idea, let me know, okay? Okay, I got a question from Danny. So Danny's idea is, how about this reaction? How do you think, guys? It doesn't work, okay? Because silver bromide is less soluble than silver chloride, right? So even if this reaction can go through the right side, you couldn't see it dissolve because you got a new precipitate, right? I mean, even it can go to the right side. So now say if you add some Br minus to the white silver chloride precipitate, it will go to this direction. But you couldn't see the solid dissolve. You will see the solid change color, but it's still a solid. Okay, Kahoot, I tried before. It doesn't work pretty well here because every time when I change the place, when I need to change my writing system and also the Kahoot system, it doesn't work. Okay, it seems like some of you like the idea. You guys can give me more feedback later, or give me some feedback by email in the Google Classroom. Okay, so we use around 20 minutes. Tomorrow, let's try to minimize the time into 15 or 10 minutes. Okay, let's start. So I hope you guys all got some chance or some time to read the questions I put here, because I definitely do not have enough time to cover everything in the handout. And if you get the handout of number 5 or number 6, there are 32 pages, which means it's impossible to finish in 2 hours, right? Especially that handout is full of calculation. So, I forgot to say one more thing. So the reason after 2 sessions, we will get 2 days off, right? So April the 3rd, April the 4th, and then the next one will be April the 7th. It's because starting from April the 7th, we are going to talk about organic chemistry. So I want you to take the 2 days, especially in the weekend, to do some reading. Otherwise, you will be lost in my class, okay? Okay, so let's start. For the easy questions, I will just write down the answer here. And for the hard one, I will do some explanation, okay? So if you finish it, you can check your answer. If you didn't, you can have a look right now. I'm going to briefly explain why I put those 4 questions in the first category, the combustion. It's because lithium is the only normal one in the alkali metal. When I say normal, which means it will produce normal oxide. And all of the other alkali metal, they will produce either peroxide or even some other weird stuff, like this. This is called superoxide. Superoxide, and for potassium, it will even change to something like this, like ozone, right? But is a O3 minus, is not ozone, seriously. So this is why we have this comparison. The second group for phosphorus, we know is a 5A group element. So when it combusted in oxygen gas, it will produce the oxide with the highest oxidation number. I think the highest oxidation number of phosphorus should be the group number 5A, right? Some of the textbook will write down into P2O5, but actually the molecular formula is P4O10. I want to briefly show you the structure of P4O10. Something like this. You can see there is a kind of tetrahedral structure made by the 4 phosphorus, and then in between each 2 phosphorus, there is a single bonded oxygen, and on each phosphorus there is a double bonded oxygen. So in total, it's P4O10. Just for you to have a look, you may not need to memorize the structure. So for the reaction type I listed here, you don't need to memorize. But the reason why I summarize here is because the more you know about the reactions, the easier for you to analyze the unknown or unfamiliar reactions, right? Or we always start from the known reactions to the unknown, the familiar one to the unfamiliar one. So this is why we want to summarize the reaction types, right? Because it's impossible for us to memorize all of the reactions, but those reactions can go to the different categories. Yeah, this is a good question. I just want to say this. So it's not SO3 because although sulfur is in 6A group, it seems like it should be SO3, but it's not because SO2 is more thermodynamically stable. So in industry, when you need to convert SO2 into SO3, actually it's not easy, it's hard because it's an equilibrium. You need to do it in high temperature, high pressure, and also catalyzed by a certain type of catalyst. So the reason why I list this reaction here is just for you to know SO2 is more thermodynamically stable than SO3. Okay, great. So this is the first category, the combustion in oxygen or in air. The second category is the combustion in other oxidants. Magnesium nitride. For the second one, I will leave it here. I want to show you a video and then you guys can have a look. So let's finish this group first. The reason I listed these two here is because I want you to compare the oxidizing ability of the chlorine gas and the sulfur. So if you have a look at their positions in the periodic table, so sulfur is here, chlorine is here, fluorine is here, oxygen is here, right? So which means chlorine is kind of behind or after the sulfur, which means chlorine is more non-metallic, right? Which means its elements is supposed to be a stronger oxidizing agent, right? Because it's easy to gain electrons because the size of the atom is smaller, right? So this is why when ion reacting with chlorine gas, it will produce the +3 ion chloride. But when the ion react with the sulfur, it will only produce ion 2 sulfide. So this kind of comparison can give you some idea about chlorine is a stronger oxidizing agent than sulfur, especially when it meets with a metal with multiple oxidation number, right? Okay, magnesium nitride, I believe you have no problem. I think I remember there's 1 year kind of burn the magnesium in the air. You will get two products, right? One is magnesium oxide, another one is the magnesium nitride, right? I will share the lab handout of this lab with you in Google Classroom later. You guys can do some reading and get more details about that lab, because laboratory is also an important part for this category. It's not only descriptive chemistry, it also includes the laboratory. Okay, I want to show you a video about magnesium combusted in carbon dioxide. So before we do that, do you have any kind of prediction about what is the reaction? So here, we are producing the carbon dioxide. You see the bubbling, right? And then you see, okay, the flame kind of turned off because of the carbon dioxide does not support the combustion, right? It's very quick. Let's have a look again. Did you see the bubbling? Probably is sodium carbonate reacting with an acid. Okay, now it's magnesium. We put it into the carbon dioxide. So you see it combusted very rigorously, right? Very wide flame, or quite similar to its combustion in the air. And then probably you already see some black stuff. I want to show you another. Yeah, this is the magnesium combusted in the dry ice. Dry ice is also carbon dioxide. Yeah, this is the magnesium on the dry ice. So you will see, it's quite impressive. Next. Okay, I think pretty much you got the answer. The product should be magnesium oxide and carbon. So in the process, there might be carbon monoxide produced as well. But the final products, especially the black solid, should be carbon. So the kind of magnesium gain the oxygen from the carbon dioxide. So David asked, what is the source of the electrons to reduce carbon dioxide? It's from the magnesium, right? Magnesium loses electrons, so the +4 carbon gains the electrons, change into the 0 carbon. Okay, so this is the second category. The next one is single displacement. I have no space to put the full name, so you guys can do the correction. This is for metals. So I think it should be pretty straightforward. I didn't balance it. And no reaction. Copper 2+ and silver, right? So the first story is for the pre-hydrogen metals. So only the pre-hydrogen metals can displace the hydrogen gas from the acids. And copper, obviously, is a post-hydrogen metal, right? So it cannot do the reaction. The last one is the relative more reactive metal will displace the less reactive metal from its source, right? Let me see what I have here. What this? Let's try. Oh, this is the single displacement. Just a video. This is when you put zinc in silver nitrate. Obviously, you got the silver tree, very pretty. It's 40 times speed. The actual speed is not so fast. Very impressive, right? So this is for the kind of the high resolution and the high speed camera. Zinc and copper sulfate, you got the copper. Okay, this is a very good website made by some Chinese guy. It's called Beautiful Chemistry. So if you got time after class, have a look. There are a lot of really funny videos. Very cool. Yang asked a great question. We are going to discuss it later. How do we know which oxidizing agent is strong enough to oxidize the ion into 3+? Okay. So next, what this? What this link? Oh, it's for next one. Okay. So for the single displacement for the non-metals, obviously you will see is Br2 and Cl-, right? Because it's a single displacement. And F2 into water, it will be oxygen gas and HF. I will talk about these two reactions later for more details. Aditya asked a question whether oxalate will reduce ion 3+ or not. No, they will make the complex. because oxalate is a pretty good bidentate ligand. We know the oxalate is like this, right? So when it meets with the iron 3+, 3 of the oxalate will bind with 1 iron 3+ to make a complex. And this complex is very stable with a octahedral structure. Yang asked whether bromine chloride, BrCl, typically I don't think so, because bromine chloride is not a very stable compound. Okay, we can discuss this question with a little bit more details later. So the last category is some typical redox titrations. So actually, this is how we accumulate descriptive chemistry. We do experiment. Because we are online class, I cannot, show you the experiment. Like what I can do is show you the video. Although sometimes the video is even better, because for some of the experiment is very time consuming. It will also produce a lot of toxic or pollutants, right? So it will be relatively easy and get some even better results, but you lose the hands-on skills. But I believe most of you will get the chance to practice in your classroom. Okay, the next one, permanganate obviously is a very strong oxidizing agent. When it is acidified, it's even stronger. So it can oxidize the oxalate into CO2. And then under acidic condition, the permanganate will be reduced into Mn2+. So do you know what is the oxidizing, not oxidizing, is the oxidation number of carbon here? Oxidation number? Yeah, pretty good, right? It's +3. And then when it changes into +4, yeah, it's oxidizing, right? And the +7 manganese change into +2. So the last one, oh my God, this is not good. I will try. Acidified permanganate oxidizing the hydrogen peroxide. We know it's -1 here. So what will be the products except the Mn2+? This is a very typical redox titration. So what is the second product? What is the product of H2O2? It should be oxygen gas, right? Change into 0. Oh, I didn't balance reaction. When I say I didn't balance, I even didn't balance the elements. For example, if you need to write down the reaction, you may need to add the H+ and add water in the right side, okay? So this is the idea, but I kind of briefly talk about what is the reaction, okay? You guys can do the balance by yourself, although you don't need to balance the coefficient, but you may need to balance what are the ions and what are the products, right? Okay, before we keep going, I would like to kind of ask you how you feel about difficulty, feel about the speed. Let me try to put a survey link. So now say, if you choose yes, it's okay. If you choose no, it's too fast or it's too slow, okay? If you think it's perfect or it's good, choose yes. If you think it's too fast or too slow, choose the other options. Great. It seems like so far so good. Most of you feel it's okay. Although a few of you choose not okay, I didn't get it's too fast or it's too slow. You can let me know, okay? So I will share the results with you. I got 18 answers. So I can only try to satisfy most of your requirements. Probably cannot satisfy all of you, okay? Let me see. Oh yeah, we can watch this two. And let's watch it right now. This is the titration, permanganate titrated oxalate. So I will just jump to 6, something like this. This is the oxalate, the acidified oxalate. And then in the burette, we have the purple solution, which is the permanganate. Oh, by the way, can you guys hear the sound of the video? Yes, oh, no, it's good, because I don't want you to hear it. Okay, so you will see previously when you add the permanganate job by job, the pink color or the purple color, it will disappear quickly, right? But when you add the last job, which is at the equivalent point, you will see the color remain and it will not disappear. Hello, Kenny, do you have any question? Okay, so let's try this, have a look at this question. Although I believe all of you tried this before, just want you to have a look. It's question number 8. Okay, got it. I will try to slow down a little bit, but probably not too slow. So try your best to catch it and also do some preparation if you got the time for the next class, okay? Okay, I think it's pretty easy, right? The answer definitely is A, because the permanganate itself is a good indicator. So we don't need to add any other indicator. So since we already talked about this reaction, this question, let's also talk about B, C, and D. So first, what will be the indicator for B? Some of you think B also does not need to use the indicator. So which means we have the chloride in the flask. Let's try it. Let me add a page. So I have a flask with some chloride. And then in the burette, let's say this is the burette, I have the silver nitrate solution. So I'm going to add the silver nitrate job by job. And then you will see the white precipitate will produce. So how can you tell the end point, Eller, since you have the question? So I will guess probably you think when there is no more precipitate produced, and then I can say, okay, this is the end point. Actually, you can't, because, right, the speed, because the chloride concentration is getting lower and lower. So the production of the precipitate is not visible. It's not visible enough for you to say, okay, this is the equivalence point or this is the end point. So we should add some chromate. And the chromate will bind with the silver plus to make a reddish brown precipitate. And then when this reddish brown color appear, and then we can say, okay, this is the end point. So let me show you what is the color of the silver. Yeah, it's something like this, right? Kind of reddish brown. So obviously it's quite different from the white color. So I would like to ask you one more question. So these two precipitates, which one do you think is more soluble? Obviously, there are two options. Either silver chloride is more soluble or silver chromate is more soluble. Okay, let me change my question. So you want the silver chromate to appear in the end of the titration, right? Not before the titration or in the process of the titration. So which means these two ions should not bind too strongly. If they have a super strong affinity, So which means the KSP is smaller, which will make the endpoint earlier. So now say even the chloride is still left, there is still a lot of chloride left, but the reddish brown precipitate already appears. So which means you cannot get the endpoint, right? So our conclusion is the KSP of the silver chloride, not the KSP, sorry, because these two, they are different types. Silver chloride is AB and this one is A2B. So now say the solubility of the silver chloride should be greater or smaller than the solubility of the silver chromate. Makes sense too? If I didn't make it clear, I can try to talk about one more time. Okay, if you guys have no question. So let's go back to that question. This is B. Oh, where's my browser? Sorry guys. Oh, it's here. So for C, obviously we should use either phenolphthalein or methyl red or methyl orange, some other common used acid base indicators, right? Oh, by the way, which is the best one here, since acetic acid is weak? So which means the endpoint is not neutral. The endpoint is basic, right? Because at the equivalence point, you got sodium acetate. So now say the endpoint is around 8 or 9. So I agree with you, phenolphthalein should be the best one because phenolphthalein has a pKa of around 9, which means it will change color in between 8 to 10, pH 8 to 10, right? I think this is standard AP chemistry. The last one is also an acid-base titration, but it's slightly different because the endpoint is acidic because it's ammonium chloride. So in this case, you probably can choose methyl red or methyl orange because these two will change color in the acidic range, okay? But I think compared to phenolphthalein, these two are not so common used or common assessed. So you may not need to memorize what is the color change range of these two indicators, but you can have a look by yourself, okay? Let me have a look at the time. Not too. Oh yeah, this is a good question. David asked whether the indicator used to be a source of error. It will be. So this is why you need to choose an appropriate indicator. For example, if the endpoint is basic and you use a indicator which change color in acidic range, which means there will be some issues, right? Oh, you are talking about that too? So we need to do some calculation. So methyl orange will change color from 3.1 to 4.4. And methyl red will change color from 4.4 to 6.2. So since the titration is like this, I would like to estimate the pH is around, let's say the concentration 0.1 mole per liter. The Ka is around 10 to -5. So we do a square root. So this is the H plus concentration, right? So it's around -3. So pH is around 3. So in this case, if the pH at the end point is around 3, I would like to say MO is a better choice, right? So it really depends. This is not KB, this is Ka. So here I put Ka. So it's kind of one. It's just an estimation. It's not a very accurate calculation. Okay. Okay. Let's go back. Oh no. Yeah, we finished this part. Nice. The second part is redox reactions and standard reduction potential. So here we listed a lot of metals with different reactivities, right? So you will see from the bottom to the top, the metals are getting more reactive. You can see it from what is the condition for the metals to react with water or to react with the acid. So let's try. I think you guys can figure it out. Oh, yeah. Oh, you guys remind me. Sorry. Thanks for the correction. Let me correct it. I made a silly mistake. So here, I shouldn't use 10 to negative 5 because the Kb of ammonia is around 10 to negative 5. So the Ka of ammonium is Kw over Kb, which is around 10 to negative 9. So I need to do some correction. So if this is the idea, it will be around negative 5. And then the pH is 5. So, okay, methyl red is the better option. Thanks for the reminding. Maybe bromocymo blue is also a good option, but it doesn't matter so much because actually we got a lot of indicators which can be used in the acidic range. Oh, okay, I got your question, David. So David's question is, let's say methyl orange is a better indicator, but if we use methyl red, will this produce a significant source of error? It will not actually, but there will be several jobs of errors. Typically, for a titration, it should be in between 1 to 2 jobs, which means when you get the end point, the volume you added is either 1 or 2 jobs less or more than the equivalence point, right? So even if you use this one for the pH 5 endpoint, it will be kind of more than 2, definitely. But we really do the calculation to see how many jobs it will be away from the equivalence point. But it definitely will produce the error. I cannot evaluate how significant it calls significant, but this is not allowed, which means you basically choose the wrong indicator. Okay, sorry about this. Okay, so obviously we'll have hydrogen gas, right? I think no question, right? The reaction is easy to understand. The barium kind of lose the electron to what? To the H plus. Where is the H plus from? The H plus is dissociated by the water, right? So this is why only those super reactive metals can directly react with water. And the other metals which are not so reactive, they have to use H plus. So basically in water, the concentration of the H plus is too low, right? So only those very reactive metals can make the reaction. Okay, since they already balanced the reaction, so I will also balance the reaction, okay? Let me see, yeah, it is balanced. So for zinc, you will see it needs to react with the water vapor, which means it's harder because water vapor, right, it will have a higher dissociation. So kind of produce more H plus. You can try to understand from this perspective. So it will produce the zinc hydroxide, which is a precipitate, and also the hydrogen gas. But this is really a very small portion. Let me show you a video. This is magnesium react with water. When you put magnesium in water, it does not react. Obviously, if you just put the magnesium in water, there is no reaction because magnesium is not so reactive. It's much less reactive than sodium, right? And then what we need to do, yes, you're right, Lucas. Okay, guys, what happened? Why the solution got into purple? Although I didn't tell you what it added, but can you have a guess? Complex ion. Magnesium is a main group element, which means even it has the complex ion, it's supposed to be colorless. Yes, you're right. We added the phenolphthalein in the system, so which means the reaction really happened, right? Because magnesium reacts with the water to produce a small amount of magnesium hydroxide, and the magnesium hydroxide will partially dissociate and produce some hydroxide, and hydroxide will make the phenolphthalein change the color, right? Makes sense? So obviously, this experiment can demonstrate magnesium is not as reactive with like barium, sodium, potassium, calcium, those very reactive metals. So this is why you see magnesium is here, and then the boundary is in between sodium and magnesium because the first five, they can displace the hydrogen gas from the water. And the second part, either they need to react with the boiling water or react with the steam. There is a question. Magnesium hydroxide is not a strong base, it's a weak one. First, magnesium hydroxide is a precipitate. So typically, if it's an insoluble base, it's not a strong base, right? It needs to be a soluble base, and then it might be strong, like sodium hydroxide, potassium hydroxide, barium hydroxide, something like that. So magnesium hydroxide is not. I would like to say, first, the steam has a much higher temperature. So this is why the reaction is relatively easy to happen. And secondly, we know that dissociation of water is endothermic. So if you heat the solution or heat the water, there will be more water dissociated, right? For example, the Kw of water at 25 degrees Celsius, that's the room temperature, is around 10 to negative 14. But the Kw at 100 degrees Celsius, I believe is greater than 10 to negative 13, although I forgot the exact value. I didn't look into this, but I can say probably those are the two possible reasons. One is higher temperature, faster reaction, and the second one is higher temperature will make the water more dissociable. Okay, and then if we keep going down, so the next group will not react with water, it has to react with the acids. Obviously, the product is tin 2+. The last one, like silver, they cannot displace the hydrogen gas from any acidic source. Okay, so there is no reaction. So here you see a hydrogen gas is here. So we use this as a boundary. We say all of the top metals into pre-hydrogen metals, and then all of the bottom one into post-hydrogen metals. I strongly recommend you to memorize all of the 5 common post-hydrogen metals, which are copper, mercury, silver, platinum, gold. And the last 2 are also commonly used for inert electrode, which means because those metals are very stable, so when you use them for electrodes, they will not participate in the half reaction. They will only be the pure electrode, which means they are the place for electrons to gain or to lose, but they themselves will not participate in the redox. Make sense? Okay, my first question, why only pre-hydrogen metals can replace hydrogen gas from water or acid? I think you need to recall the standard reduction potential because only those metals, their standard reduction potential is smaller than 0. What is 0? 0 equals to the SHE, right? The standard hydrogen electrodes, right? So if it's more negative, which means it's more reactive, because more negative means easier to lose electrons. I don't know, does this make sense to you? Because, you know, this is a very important question. If this kind of stuff doesn't make sense to you, which means our, not next class, our second last class will be very tough because this is something related to the chemical principles. Let me have a look. Pre-hydrogen metals are oxidized with positive standard cell potential. Kind of. Yes, you are right. Basically, is the E cathode standard is greater than the E anode, and then the E cell standard is greater than 0, and then the delta G standard is smaller than 0, and then is spontaneous. I hope it makes sense to all of you. Next question. May I ask you to have a analysis? Can any of you? Okay. So when you put zinc, silver got reduced, copper got reduced. Zinc will react with water. Zinc is not so strong. Zinc need to react with, steam, water vapor, which means zinc will not react with water. So my question is, zinc will prefer to react with copper 2 plus or react with silver 1 plus? And why? So my answer is silver 1 plus, because the one with the higher standard reduction potential will be first reduced. Make sense? Right? Here you see silver is less reactive than copper, so which means silver plus is a stronger oxidizing agent than copper 2 plus. Make sense? See, you guys can have a look. I will be right back. I just need to get more water. Yang asked the question, nitrate. Actually, when there's no H plus, nitrate is something which is very stable. So which means nitrate is not a very strong oxidizing agent. So only when there's H plus, the nitrate kind of changes into nitric acid, and then it's a strong oxidizing agent. Okay, so obviously, so the reactivity is getting stronger down the group of the alkali earth metal, right? I think it's easy to understand. This is called periodicity, right? Sodium, magnesium, aluminum. How do you guys think? Sodium obviously is the most reactive one, right? So which means it's getting weaker. How to interpret this? Sodium, magnesium, aluminum, they are in the same period, right? So across the period, the mortality or the ionization energy is increasing, right? No problem. So basically, sodium, when you put it in water, it reacts rigorously. Magnesium, you need to have the boiling water, and the aluminum typically cannot do the reaction. You may need to use the steam. How about these three? Copper, silver, gold. Yeah, the reactivity is also getting weaker, right? Down the group. So this is something a little bit weird because in the main group elements, we say down the group is more reactive, and copper, silver, gold, they are also in the same group, but they are getting weaker, right? I'm not pretty sure how to do the explanation, but we do, have the results, the conclusion, right? Because we know gold, this is common used as the money, right? It's because it's super stable, right? And copper is relatively easy to be rusted. Nansenite contraction, it might be related. Okay, guys, let's leave a question here. I will try to do some homework and then try to figure out. I'm not sure about the size. Okay, let's leave it here. I'll try to use the class time to talk a little bit more, and I can share the answer or at least the results of my homework with you guys later next time. It might be related with the Nansenite contraction. If their size are similar, it should make sense, because if their size are similar, gold obviously has more nuclear charge, which will make the ionization energy higher down the group, right? So maybe Nansenite contraction is a good explanation. Yes. Okay. So you see, copper, silver, gold, they are all used as money in the history, but obviously gold is gold, right? Gold is the most valuable one. It's not just because gold is less in the earth, it's also because gold is more stable, right? Next one, finally, we got this question. We already analyzed it will produce the ion 2 plus, not the ion 3 plus. What is the reason? If you have a look at this reaction, you will see, based on these two values, can you calculate this? Definitely you can, right? But today we are not a calculation focused class. So I'm not going to give you the time to do the calculation. This one, the standard, the E standard is around 0 volts, very close to 0 volts. So you will see, compared to this value, can you tell me it's relatively easy to oxidize the ion into ion 2 plus or ion 3 plus based on these two values. Yeah, I think it's quite obvious, right? The ion 2 plus is more readily to be formed, right? Yes, you guys are right. You cannot directly, get the average or do the addition of subtraction, right? You need to think about the number of electron transfer because you are going to use Gibbs free energy as for the Hess law, right? Which means the delta G equals to negative NFE. We got a lot of chance to discuss this later. So, next question. How does the reactivity affect the attraction of metals from their ores? So let me ask you a question. If a metal is more reactive, is it more likely to synthesize the metal by electrolysis or less likely? If the metals are more reactive. Not just, ask you this question. Mm. 39. I believe you guys all finished those kind of questions, but just to get the chance to review it. Right? I think it's pretty straightforward, right? The answer should be A, aluminum, because it's the most reactive among these four metals, right? Obviously, gold, you don't need to use electrolysis because you can use the physical method, right? You go to San Francisco 100 years ago, you probably can pick up a lot of gold on the ground. Right now, probably nothing is left. Okay, F, I think you guys read my question, right? So the reaction should be sodium plus under a certain temperature. This is the reaction, right? Can you guys tell me what is the driving force of the reaction? Does it mean sodium is more reactive than potassium? Since sodium is displacing the potassium. Yes, you guys are right. The driving force of the reaction is the production of the gas, or you can say the entropy is increasing, right? Delta G equals to delta H minus T delta S. So if delta S is positive, a relative higher temperature will drive the reaction, right? No problem. So this reaction cannot demonstrate sodium is more reactive than potassium. So my next question is, why under the same temperature, potassium is a gas, but sodium is a liquid? We know how to analyze the melting or boiling point of the metals, right? Because we can use Coulomb's law based on the electron C model, right? So sodium and potassium, they are in the same group, right? They are in the same group, so which means potassium has a larger size, so the Coulomb's attraction is smaller, which means the nucleus of the potassium kind of attract the valence electron a little bit loosened, right? So the attraction is weaker. So this is why down the group, lithium, sodium, potassium, rubidium, cesium, its boiling point is decreasing. Makes sense, right? A lot of energy released when sodium chloride made and potassium heats up and bios. I didn't get the bios, but I think the other part boils. Okay. The other part I think makes sense, but the major reason is still potassium has a lower boiling point than sodium. Okay, my last question in this page, post-hydrogen metals like copper and gold react with acids? Typically, no, but actually it can, right? We can use like oxidizing acid, which we are going to discuss on next page. We can also use aqua regia, right? The mixture of concentrated nitric acid and hydrochloric acid, right? Okay, how about the speed right now? Is it okay? If it's good, we'll keep going. David asked a question. When we say a metal is more reactive, which means the reduction potential is more negative or less positive? Because when it's more negative, which means it's relatively easier to lose electrons. Based on physics, the electrons always move from the lower potential place to the higher potential place, right? So if an electrode has a lower potential, which means it's easy to lose electrons. Typically, I will recommend my student to try to understand this problem based on physics, right? We know the current is like the water flow. It's always flow from the higher potential to the lower potential. But the electrons are negative, so it's just move in the opposite direction. It will move from the lower potential to the higher potential. I hope it makes sense to you. Okay, so metals reacting with acids. Pre-hydrogen metals, they will react with strong acid to produce the hydrogen gas. It's even not necessary to be strong. If it's weaker, it can also produce a hydrogen gas. Here, I just want to make it easy. Put the strong acid. And if it's post-hydrogen metals, like those 5, there's no reaction because their standard reduction potential is greater than 0, right? Although theoretically, you can try to increase the concentration of the acids, right? According to the Nernst equation, there is always a chance for you to make the potential of the H+ hydrogen gas very positive, right? But there is always a limitation because the acid cannot be kind of, very concentrated, right? There is always a solubility limitation. The right part, obviously, is harder. If we use something called oxidizing acids, such as concentrated sulfuric acid, concentrated nitric acid, dilute nitric acid, they are all called oxidizing acid. So no matter it's pre-hydrogen metal or post-hydrogen metals, they both have the reaction. So the thing we need to care about is what is the reducing products of these 3 oxidizing acids. Do you know what is the products of the S2 H2SO4 sulfuric acid? Yes, it's a air pollutant. It can also be used to bleach what this car is called Fuchi sign. This is kind of a dye or an indicator. It's pink, but the SO2 will bleach it, will make it colorless. So you guys can try to find the video by yourself, but actually not so common used in chemistry. Bleach means kind of make it colorless, decolorize. So I just, put it here. Actually, you can delete it. Not so important. How about this thing? Oh, before we discuss this, let's have a look at a question. Number 4. Don't answer. I want to ask you guys. Let's have a polling. Stop sharing and yes, relaunch, continue. Yeah, give you guys 10 seconds. Okay, I got 16 answers. If you guys finished, I'm going to share the answer with you guys. Okay, 18, no more. Okay, the answer is C. The product is, oh, wait a second. So many of you choose ammonia. We are talking about question number 3. Did I tell you question number 4? Are we working on question number 3? Oh, okay. Oh, sorry. Let's do it again. Let's work on question number 3. Sorry guys. It should be question number 3. Okay, pretty much here. The answer should be D, which is nitrogen monoxide. If you choose A, which means you didn't get silver, is a post-hydrogen metal. Post-hydrogen metal cannot displace the hydrogen from an acid, okay? Ammonia is also wrong. First, ammonia cannot be released from an acidic solution because ammonia will be protonated into ammonia in acidic solution, right? Although from the perspective of redox, ammonia is kind of reasonable because the oxidation number of nitrogen is decreasing from +5 into -3. Okay, so let's have a look at another question. Question number 7. I believe I didn't make a mistake this time. Okay, we got 18 answers. Most of you choose C. C is the correct answer. A few of you choose A. Probably you think HF is a very special assay. Actually, HF is special, but the special thing for HF is it can react with silicon dioxide, which means it can react with glass. So this is why the hydrofluoric acid need to be put in a plastic bottle rather than a glass bottle. But it's a weak one, so it cannot react with the, oh, we didn't specify the metal here, but if the metal is strong enough or reactive enough, it produces hydrogen gas. It will not produce anything else. So a few of you choose D. Sulfuric acid is very special. If you go back to this, you will see dilute sulfuric acid is a regular strong acid. But did I show you the results? No. But the concentrated sulfuric acid is a oxidizing acid, which means it will not produce hydrogen gas. It will not produce hydrogen gas. Okay, so the answer should be nitric acid. So when it's diluted, it will produce NO, which is colorless. When it's concentrated, what is the product here, which is reddish brown? Yes, it's NO2. NO2 is reddish brown. Okay, let's answer this important question. So why the oxidizing acid will not produce hydrogen gas? Let's take nitric acid, for example. Actually, it's because this value is much greater than this value. So which means nitrate under standard condition, when I say standard is H plus equals to 1 mole, is a much stronger oxidizing agent present in the system. So it will be reduced rather than the H plus, right? So here I want to specify when I say those acids are oxidizing acid, I'm not talking about those two acids are not oxidizing acid. They are also oxidizing acid, but they use their H plus to show their oxidizing ability, but not the anion, not the anion. There is a strong, but it isn't NO unstable because it is a free radical. Yes, NO is unstable. It will be very easy to be oxidized into NO2 in the air, but it doesn't affect NO is initially produced under dilute nitric acid, okay? So oxidizing acid we want to specify is just the anion is oxidizing, is not the H plus, okay? I hope I make it clear. Next, I'm going to show two more videos. One is the penny dissolved in the concentrated nitric acid. By the way, is this legal or illegal in the United States? We kind of, get the excuse doing science and destroy the money. Okay, I think it's pretty clear. Oh, sorry. I think it's pretty clear. We add the concentrated nitric acid to the penny, and the penny is an alloy. It's made by copper and zinc. It's not pure copper. It's copper and zinc, and also a very small amount of the other metals, but mainly copper and zinc. So zinc will be oxidized into zinc 2+, which is colorless. and copper will be oxidized in copper 2+, which is supposed to be blue, but here is a little bit green because there's also some reddish brown NO2 dissolved in the solution. So this is why you have yellow and blue. The mixed color is green. So I think I answered Michael's question. And obviously, the reddish brown gas is the NO2, right? Okay. This is also a very typical experiment in AP chemistry, how to use spectrophotometer to measure the mass percent of the copper in either in the penny or in the brass. Brass is also an alloy made by copper and zinc. So yeah, this is the first one. The second one is copper reacting with concentrated sulfuric acid under heating. This is concentrated sulfuric acid. Already put some copper into the acid and heat by the Bunsen burner. I think you already observed the bubbles on the surface of the copper, and actually the copper changed color. It changed from kind of red into black, right? So which means there is a reaction ongoing here. The bubbles is SO2, and then after a long time, you will see the solution change into a little bit green, but it's also not blue. But after you finish the experiment, you add some water in the system, the solution will be blue. Yes, the heating is very important for this reaction. If you do not heat it, the reaction is very, very slow. Kind of concentrated sulfuric acid is not as strong as the nitric acid. If you put the copper in nitric acid, typically you don't need to heat it. But if you use dilute nitric acid, you probably need to heat it. So it also depends on the concentration. Actually, this reaction is very complicated. We just want to make it easy here. Okay, keep going. So I have extended the question here. So now say you have carbon react with the sulfuric acid, which is concentrated. And then we probably need to heat it. What will be the product here? Oh, this reaction cannot be ionic because concentrated sulfuric acid kind of almost have no water. So most of the sulfuric acid is not dissociated, okay? Yes, you guys are right. Carbon will be oxidized into carbon dioxide. Sulfur will be reduced into sulfur dioxide. And then we also have the water. And if you replace the sulfur, replace the carbon by sulfur, you will get both SO2 and SO2, right? Make sense? Okay, number 4 is something you probably never see in an English textbook. This is summarized by myself. Actually, I removed a lot of reactions. I don't know whether you guys worked on this or not. So I will quickly write down all of the reactions, and then you guys can let me know. Question 1, reaction 1 to 9, which reaction you want to have a discussion, okay? Okay, guys, I'm done. You guys can have a look and let me know. 1, 2, 3, 4, 5, 6, 7, 8, 9. Which one you need me to have a analysis? Yeah. You guys can give me a little bit more feedback. Okay. Eller, you asked a good question. I can answer you later. Yeah, I think Yang answered the question. Okay, seems like you guys want to know number 3 and number 4. Number 3 actually is a question from National Part 2 in 1 year, and the answer key of the other year is wrong. So the reaction can be interpreted in this way. So you have the sodium peroxide reacting with water. So let's do a double displacement first. When we say double displacement, here you have sodium plus and you have peroxide. Here you have H plus, you have hydroxide. So they will change their partner, right? So the sodium will bind with the OH, get into sodium hydroxide, and the H plus will bind with the peroxide to produce the hydrogen peroxide. So if you need to balance reaction, you can do it in this way. So this is the first step. But this reaction is very exothermic. So it will produce a lot of heat, which will make the hydrogen peroxide unstable. So it will decompose into water and oxygen gas. So if we combine these two reactions together, you'll get something like this. I remember that year, the answer key is something like this. I cannot say it's not reasonable at all. It's a kind of a little bit reasonable because the answer key kind of think about hydrogen peroxide. First, it will not decompose. It will be very stable. Actually, this is not true because this reaction will release a lot of heat. And we know hydrogen peroxide is very unstable. It needs to be stored in the refrigerator, right? And secondly, it also think about the hydrogen peroxide is a strong acid. So obviously it's not, right? Hydrogen peroxide is slightly stronger than water. So if you check the pKa of the hydrogen peroxide, is around 11.75. So which means it's kind of 100 times stronger than water, but it still is not a strong acid. Is even not a acid we typically think. So it's not reasonable to write down the products into HO2 minus, which is the conjugate base of the H2O2. Number 4 is kind of similar. So obviously you can think about the CO2 want to gain a O2 minus from the peroxide. So it's a kind of the O2 minus disproportionate into O2 minus and oxygen gas, right? So this is a new reaction. I think you probably didn't say it before, but I believe it makes sense, right? Can you guys still hear me? It seems like my earpod is out of battery. Okay, so I will completely take it off. Great. You guys can still hear me, right? Okay, nice.
And then let's have a look at another question. Oh, guys, let's leave this question until tomorrow, okay? Because tomorrow we are going to focus on the non-redox reaction, and the comparison of these two reactions will be my point, okay? So I can leave this question for you to think about for a while, why we can use the same reactants to produce the different products. Let's make it slightly clear. So here, this is the access. Here, this is the access. I hope it will be helpful for you to do more homework after the class, okay? If you guys have no more question, I will move to another part. Oh, by the way, so we are going to learn 3 representative metals, and sodium is the representative, the reactive metals. So if you know about the reaction of sodium, you pretty much know about like potassium, barium, or all of the other stuff. I got a question. Number 7, where did the lime water come from? The lime water, you add the calcium hydroxide saturated solution is called the lime water. So you just add the lime water into the solution of sodium carbonate, and then the reaction will be driven by the production of the precipitates, and then you get the sodium hydroxide. So this is a little bit weird. This reaction is a little bit weird, but it makes sense. Okay. The second representative we are going to learn is amphoteric metals. We are going to use aluminum as a representative. So I will use a similar strategy, write down all of the reactions. Does this work for you? I write down the reactions and you check it, and we discuss those questions you don't know. You guys can always let me know, okay? I'm done. There's no reaction 4, so I skip it. Oh, there is a reaction 4. Oh, sorry guys, I made a mistake. Which question you would like to know? Oh, there is another one. Oh, sorry, guys. Okay, I got a few questions. The first one is what difference between reaction 4 and reaction 6? Obviously, they are different. Reaction number 4 is aluminum oxide. Reaction number 6 is a aluminum hydroxide, right? So aluminum oxide is an amphoteric oxide. Aluminum hydroxide is an amphoteric hydroxide. But the mechanism is pretty much the same, right? Is a kind of, is driven by the production of water. Water is a weak electrolyte. So this is why this kind of, oxides or hydroxide will dissolve, right? And then, okay, number 4, still number 4 from Kelly. So let me briefly talk about the mechanism, although we are going to talk about this tomorrow. So you can think about the real driving force of reaction is like this. This makes sense to you? It's a kind of, this is a strong acid, which produce a relative weaker acid. And then this is a strong base, which produce a relative weaker base. Number 8. Number 8 is very common for the kind of insoluble hydroxide. Most of the metal hydroxide, if it's insoluble, typically is not very stable under heating. So when you heat it, you will get something like this. You will get something like this. For example, magnesium hydroxide, copper hydroxide. Let's have a look at the video because copper hydroxide, probably you can see something. This is bad. So in the test tube, there is some blue copper hydroxide, which is the precipitate. And you use the water bath, actually the boiling water, to heat it. Did you see some black stuff produced? What is that? That is the copper oxide. Copper oxide is a black powder, black solid. And then you see the blue color change into more and more lighter. And then there is more and more black powder, black solid produced. So this will be a good demonstration about the decomposition. But actually, this is very common. Not only copper hydroxide, magnesium hydroxide, aluminum hydroxide, all of those insoluble hydroxides will have the decomposition. Number 6, octahedral complex. Number 6. What do you mean, octahedral complex? Do you mean the hydration? The Al3 plus is hydrated by the water? Yes, you're right. But typically, we do not write down into that way. These two are the same. I just want to make it easy because all of the metals in water is hydrated, especially for the transition metals. Okay, No more question? For some of them, we are going to discuss a little bit more mechanism in the class tomorrow, because most of those reactions are not redox, they are non-redox. So I probably will leave the aluminum triangle to tomorrow, but I can briefly write down here for you to get something today. Okay, you guys can take some notes and then try to think about how to do all of the convolutions. There are 1, 2, 3, 4, 7 arrows in total. Let's leave this to tomorrow, okay? Give you about 10 more seconds for you to finish the note taking for the triangle. Okay. And then the last representative of metals is iron. Iron is the representative of the transition metals because typically they have multiple oxidation numbers, not like aluminum and sodium is only +1 and +3. Guys, you guys can think about and have a look and let me know what are your questions. And to go to the restaurant, I'll be right back. It seems like you guys have no question. Okay, number 6. Okay, okay, great. Okay. Guys, you don't have to copy all of the answers right now. I will share this kind of annotated, handouts in Google Classroom later with you guys. Lucas, your question actually is important. We're not going to memorize all of those reactions, but for most of them, you can try to analyze it. And let me give you a few examples. Let's have a look at reaction number 9. You want to change the ion 2 plus into the ion 3 plus, which means you need to add a oxidizing agent, right? So what is the best oxidizing agent here? Since it's ion chloride to ion 2 chloride to ion 3 chloride, so the best one is just the chlorine gas or chlorine water, right? Because there is no other impurities produced in the system. And for number 10, you definitely need to add a reducing agent, right? So ion is the best one, right? It will not produce any other impurities in the system. But there are a few kind of not so easy to analyze the reactions. For example, number one, this is a very special case. Actually, if you know a little bit more about this kind of complicated oxide, it's not a mixture, it's a compound, but you can analyze it into ion 2 oxide and ion 3 oxide, okay? Let me try to answer your questions one by one. First, number 6. Number 6, actually not very hard. I want to show you a video. But before I show you the video, let me try a problem. Question number 7. Don't answer. I'm going to add a polling. Question number 7. I got 13, 14. Uh, 16. Let's wait for 1 or 2 more. Okay, 19. Wow, this is the highest answered question. Let's have the last one. Is the last one myself? No. There is one more student. Okay. Now stop here. So the answer is A. Is not colorless. First, there is pretty much no colorless solid unless it's transparent, right? You can say it's a white solid, but it's not a colorless solid, okay? Let me show you what is the color. So there are 2 test tubes. In the left test tube, there is some ion 2 plus. In the right one, there is some ion 3 plus. Actually, their color are slightly different. Although, since they are both very diluted, you couldn't see too many differences. Ion 2 plus is pale green. Ion 3 plus is kind of, yellow or something like that. It depends on the concentration. Okay. So we add some sodium hydroxide. So I think we answered that question. First, ion 3 hydroxide is reddish brown, right? The right test tube. And ion 2 hydroxide is not green. Itself is white, but is very easy to be oxidized since there is some dissolved oxygen gas in the water. So the iron 2 hydroxide will be oxidized into green first, and then after you keep for a while, it will be darker. Let me show you another video. Okay, this is the iron 2 plus solution, very pale green. And then we add some hydroxide, drop by drop. You can see previously the precipitate is almost white. And then it quickly changed into kind of green, and then yellow, and then finally the color is getting darker and darker. Iron 3 hydroxide is reddish brown. And then let's go to the end. You will see it changed into the iron 3 hydroxide. Pretty much the reddish brown color. Okay, let me see. I may have to extend to kind of 2 or 3 more minutes. Let's finish the few questions you guys have, okay? Does this work for you? The initial white precipitate is the iron 2 hydroxide. The green one is probably is something in the transition. We're not sure what that. Let me see. Yeah, so we are talking about reaction number 6. Reaction number 6 is exactly what you see when you add the hydroxide in the iron 2 plus. First, this one is a kind of white. And then it immediately changed into green. And then finally, it changed into the reddish brown. So this is the whole process. Let me see, did I answer all of your questions? I think pretty much. Oh yeah, this is a good question. We already answered this question in the beginning. Iron cannot be oxidized into iron 2 chloride by chlorine gas because chlorine gas is a super strong oxidizing agent. We put the answer here, if you still remember. So it's not like this. Okay, guys, obviously we didn't finish it. We leave kind of 2 more parts and several practice problems. Yeah, so, oh, there is something wrong with my handout. I need to do some revision. But in the end, there are some challenging practice problems. So I wish you could find some time to practice them before our session tomorrow, okay? But it really depends on you. If you got the time, try your best. If you don't have, it should be fine, right? So before we end the class today, I want to kind of listen a little bit more feedback from you guys. So how do you think about the challenge and the class in general? So let's say, okay, so let's say A you think is very challenging, and B slightly kind of 5, 4, 3, 2, different degree. So could you please give me kind of some feedback? How do you think about the challenge? So A is 5, the highest, very high. It's very high for you. And B is 4, and C is 3, and say D is 2. Okay, thank you guys. Thanks for your feedback. I will share your feedback with all of you. So it seems like most of you choose B, kind of is challenging, but not super hard. This is good, right? This is my expectation. I hope you will not feel too hard, but still we got a few you guys think is too easy. But this will be the case because this is a group lesson, so everyone has different background. So probably we cannot make everyone happy enough. So, but I will try my best. Okay, I think it's okay. Maybe I can ask you one more question. How satisfied you are? Now say 5, 4, 3, 2. It's okay. I don't know. I couldn't see any of you, so it's fine. So you feel free to say no if you didn't feel that. Okay, we got a lot of feedback. Yeah, I think it's not too bad. I will give myself like 85 points, right? Which is not too bad. Probably the following sessions will be slightly more challenging than this one because this is just the first one. I got a few more questions from you guys. Let's go through them one by one. Okay. First, you guys are curious about how you are graded in the national exam. First, there is no official information from ACS, but people all believe. So if you want to get top 150, only the part 1 will be considered, which means you only need to care about multiple choices. But if you want to be top 50, they will combine part 1 and part 2. It seems like there is a formula. So part 1 will be multiplied by 1.25 and add part 2. So which means the total point is 60 times 1.25 plus 100, and then it turns into 175. And if you want to be top 20, it will consider all of the 3 parts. And P1 times 1.25, P2, and plus P3 times 0.5. Okay, guys, my pencil doesn't work. So it's P3 times 0.5. So the total point is 200. So you guys can use different strategy to prepare for your goal. Let me see. Seems like I got a lot of other questions. Yes, for the remaining contents we didn't finish today in the first handout, I would like to ask you guys to do some homework today. And then I will try my best to quickly finish them in the beginning of tomorrow's class, okay? Let me see. So we are not going to skip the Pull-Bakes, Latimer, and Frost diagram, and also the iodometry and the other contents, okay? Okay, some of you said we need to be a little bit faster. Yes, the last part is only 25 points because its original score is 50 points, but we need to multiply by 0.5. A typical score for top 150, you need to score around 42 points out of 60. This is the experience based on last year and the year before last year. So I would like to say, if our camp does not, work so significant, which means we will not bump the grade too much, I think it will be still around 42, roughly. For top 50 and top 20, we have no clear idea. But according to my personal experience, if you want to be top 20, you probably need to be higher than 165. Yes, I'm going to post the full annotated version of the handout. So, okay, guys, let's stop here. If you have more questions for the first handout, feel free to send me email or ask the questions in the Google Classroom. Okay, let's stop here. You guys probably have to go. Thank you so much. I think we did a good job for the first class. Thank you. Bye-bye, guys. So see you tomorrow, guys.